Hello friends, I welcome you all in this video. In this video, I am going to start a course named as Linear Algebra and the paper number is 13. Basically, this course is for the students of B.Sc TY Mathematics and I am going to cover the points of linear algebra as per the syllabus of Swami Ramanand Teerth, Marathwada University, Nanded. So let's go ahead. Let's see some introductory parts of linear algebra. So linear algebra is one of the widely used mathematics in real life as well as in mathematics. It has many applications like in traffic flow, cryptography, graph theory, in coding theory, in linear programming, in signal analysis, as well as in graphics, facial recognition. Also, there are other fields in which we are going to use this linear algebra, right? So basically in linear algebra we are going to study the spaces. We call it a vector spaces, okay, and it has its own importance. And the vector spaces arises as a solution set for many problems. For example, if you see the solution set of system of homogeneous equations, it forms a vector space. Means solution set of system of homogeneous equation forms a vector space. As well as one can observe that the solution set for differential equation also forms a vector space. And basically in this chapter we are going to discuss fundamental notions of linear algebra, and those notions are nothing but linear dependence, basis and dimension. And these three notions are used in other fields of mathematics, and which are very important tools for the other branches of mathematics. So basically the preliminaries for this linear algebra course are nothing but group. As we know that group is nothing but a non-empty set with a single operation, which has to be a binary operation with three other properties. First one is associativity with respect to that given operation, and identity, existence of identity you can say, and existence of inverse. Okay, then that non-empty set with that given operation is called a group. And one should know the basic theory or basic ideas of groups, their examples, and there is some theory one should know before going to study the linear algebra. As well as one should know ring and field. As you know the field, then automatically you must know ring also, because vector spaces are nothing but we are going to define it over a field. That's why one should know what is meant by field here. So field is nothing but what? It's a commutative division ring, or in other words one can say that field is nothing but it's a group with respect to two operation. Means it's a commutative you can say it's a abelian group with respect to addition, as well as it's an abelian group with respect to multiplication. Means it has a two operation. Obviously in ring as well as in field there are two operations. Okay, but field is what? Field is nothing but it's a non-empty set with the two operation, addition and multiplication. And with respect to addition it forms an abelian group, as well as with respect to multiplication it forms an abelian group. And there is a relation between these two, plus and dot, that is distributivity. Left distributive and right distributive law must hold, then that set is called as field. Okay, so one should know the basic theory regarding this group, ring and field. These are the preliminaries required for the course linear algebra. So let's go ahead with the definition of vector space here. Vector space is nothing but what? It's a non-empty set. First of all, it should be a non-empty set, and it is said to be a vector space over a field F. over a field F if what, if V is an abelian group. If V is an abelian group, under the operation we denote it by plus. That means it should be an abelian group with respect to addition. And one more property, one more operation is there, and that operation we call it an scalar multiplication operation. Let's see what it is. Alpha is in F is a field here, and V is in V. Then we can define the operation between alpha and V, and that resultant element after multiplying alpha with V, that should be in V. Means if you are taking scalar from field and V is from V, then their multiplication should be in V, and it should satisfy some other properties, other 4 properties. That means first property is what, alpha into V plus W is same as alpha V plus alpha W, first one. And second one is alpha plus beta into V. That means you are distributing that V over alpha plus beta, so alpha V plus beta V. In the same way, other third property is alpha into beta V is same as alpha beta in bracket into V. And last one is 1 into V is same as V. You can observe here this 1 is an element of field here, or instead of element it's an identity element. Okay, and this should happen for all alpha beta in F and V and W is in. That means a non-empty set V with these abelian group with respect to addition, and alpha is in F, V is in V, then alpha V is in V, subject to these 4 properties, then and only then this V is called a vector space. Right, this is the definition of vector space. Basically what is vector space? It should be an abelian group with respect to addition, and with respect to scalar multiplication it should satisfy these 4 properties. That's it. So let's see some of the example, or first of all let's see what is there in the oxime 1. You can observe here in the oxime 1 this plus operation. This plus operation is an operation of what? Operation in V, because you are adding the vectors here. But if you look at the left right hand side of this equation, this plus sign is what? This plus sign is in again V. But in the second case here, in the second law, or you can be in second oxime, this alpha plus beta, this plus indicates an operation addition which is in F. Right, that is I have written here. Right, also we are going to use some notations. We are going to fix some notations. So up to this, and afterwards we are going to use F as a only field, and lower Greek letters will be the element of F. That is alpha, beta, gamma. We denote those elements are the element of field here. And capital Latin letters will be denoted as a vector spaces over F. And lowercase Latin letter will denote elements of vector spaces. That is V, W, U. Okay, those are the elements of vector space. Now if we ignore the fact that V has 2 operations defined on it, view it at for a moment merely as a Boolean group with operation plus, oxime 1 states nothing more than the fact that multiplication of element of V by fixed scalar alpha. Right, in basically what is happening there we are going to this scalar multiplication is nothing but one kind of homomorphism. Right, homomorphism from V to V. And how we are going to define it? Alpha from V to V is nothing but alpha into V is same as, means alpha of V is same as alpha into V. That is the homomorphism that they are saying here. So let's see the example. One can observe here that, so one basic example is that every field is a vector space over itself, and for that I can make a general statement. So that general statement is here. Let F be a field and K be a field which contains F as a subfield. See here, K is a bigger field and F is a subfield of K. Then we can consider that K is a vector space over F. Means I can say that every field is a vector space over its subfield. That I can say here directly. Alright. Now using plus, now how it happens, that we must see here. Right. Now as K is a field, it is an abelian group with respect to addition. Right, that is okay. Now the next thing is what? Next thing I want to define is scalar multiplication. That means if you consider the element F, element alpha in F and element V in K, automatically F is a subset of K. So alpha is an element of K here. So if alpha is an element of K and V is an element of K and K is a field, so I can define the multiplication operation there, because K is a field, so there is already defined a multiplication operation. So we can consider that operation as a alpha into V here, right? So alpha into V to be the product of alpha and V as elements in the field K. Now with respect to those operation, automatically what happens, this these four properties or four axioms of vector space satisfied by all the elements of K here. That's why what happens, K becomes a vector space over a field F. Right, you can see here again. So axiom 1, 2, 3 for vector spaces are consequences of right distributive laws and left distributive laws. Okay, and other laws holds automatically because K is a ring. Right, K is a ring because every field is a ring, that we know. So in general what I can say, every field is a vector space over itself. Right, let's go ahead. Now let's see in example that R is a set of all real numbers which can be which will be a vector space over set of rational numbers, because Q is nothing but a subfield of R. That's why I can say that this R set of all real numbers forms a vector space over Q. In the same way, set of complex numbers C, set of complex numbers forms a vector space over Q as well as vector space over R. Right? Yes. Now next example, in high school geometry, a vector space, vector in a space is represented by a directed line segment. Right, generally we denote a vector by a directed line segment which is from origin, that is line segment which is specified by distinguishing its endpoint. Its length is magnitude of the vector. Then two directed line segment equal length and in the same direction represents the same vector. Means when we can say that two directed line segments are equal if their directions are same and having same magnitude, then we can say that two vectors are same or equal. Okay, now what is the addition of two vectors here? Sum of two vector is by using the parallelogram law. Okay, that is there. Yeah, we have learned it already. That's why with respect to that parallelogram law, one can say that the with respect to that addition, that set of all vectors forms a abelian group with respect to addition, that whatever the sum is defined here like this by using parallelogram rule. And what about scalar multiplication? If you consider alpha, lambda in R and V is a vector, then lambda into V is a vector parallel to V. But changes will be there. What will be the changes? Changes is nothing but its magnitude will increase by mod lambda. That's the only difference between V and lambda into V. So this is a scalar multiplication. Right, now with respect to this scalar multiplication and this addition sum, this set of all vectors forms a vector space over a field R. Now let's see one general example of vector space. That general example is nothing but this one. So F be a field and V be this set of all totality of all ordered n tuples, means set of all ordered n tuples of this form bracket alpha 1 comma dot 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 alpha n, where all alpha i's are in F. Then two elements of this kind alpha 1 alpha 2 alpha n, two elements of this kind are said to be equal. When we can say that these two are equal? Whenever alpha 1 is same as alpha 2 is same as beta 2 and so on dot dot alpha n is same as beta n. That means in short alpha I is same as beta I for all I equal to 1 2 3 up to so on dot dot n. Means when we can say that these two ordered n tuples are equal whenever their corresponding coordinates are same. Now we are going to show that this V forms a vector space over F. Okay, and for that purpose we must define the addition operation over V and then scalar multiplication by element of F with element of V. So let us define first the addition operation alpha 1 comma r and so on dot dot alpha n plus beta 1 comma up to so on dot dot beta n is same as, means we are doing addition here. So alpha 1 plus beta 1 comma alpha 2 plus beta 2 comma and so on dot dot alpha n plus beta n. This is the addition. What about scalar multiplication? If you consider a scalar, say gamma, which is the element of field, and obviously this is the element of V. If I multiply this, how I am going to define it? The definition is like this: multiply this gamma with each coordinates, that is gamma alpha 1 comma gamma alpha 2 comma and so on dot dot gamma alpha n, for gamma is in field. This is a scalar multiplication. Now we verify that these operations V forms a vector space with these two operations. So what is a vector space? Vector space is nothing but it should be abelian group with respect to addition, this addition, and with respect to scalar multiplication it should satisfy the four other auxets, right? So first let's see how it is an abelian group with respect to addition. Now clearly V is closed under the addition, because if you consider the two elements, say V1 and V2, then their addition will be again an element of V. That's why it closure property holds automatically, directly, you can say. Now what about commutativity here? Now commutativity means what? V1 plus V2 is same as V2 plus V1. So consider here V1 is here and V2 is here. So I am doing addition here. Addition will be what? Coordinates twice addition, alpha 1 plus beta 1 comma alpha 2 plus beta 2 comma and so on dot alpha n plus beta n. But this alpha 1 beta 1 alpha 2 beta 2 alpha n beta n are all the elements of field here, or the elements of field here. That's why in field commutativity property holds. So I can write down this alpha 1 plus beta 1 as beta 1 plus alpha 1 comma beta 2 plus alpha 2 and so on dot dot beta n plus alpha. Hence what I got there, directly I can write down this again. There is that what I can say, which is equal to here, which is equal to V2 plus V1 here. Okay, so here we have proved the for any two vectors in V, V1 plus V2 is same as V2 plus V1, right? Yes. So let's go ahead again. Now the next property that I want to prove here is, since it's here, since all alpha is beta is are the element of F, they can commute, thus we can write down directly V1 plus V2 is same as V2 plus V1. Now let's see for the associativity. It's the same way. For the associativity, if you consider the three element of V, then their addition will be, see here, V1 plus V2 in first bracket, means addition is defined here. So alpha 1 plus beta 1 comma and so dot dot alpha n plus beta n plus In second bracket this V3 is there. Now as this is one element of V and this is another element of V, one can add these coordinate wise again. Now alpha 1 plus beta 1 plus gamma 1 comma alpha 2 plus beta 2 as it is plus gamma 2 and so on dot dot alpha n plus beta 1 in bracket plus gamma n here. Now again if one can observe here that this alpha 1 beta 1 gamma 1 is are the element of field, but in field with respect to addition it is an abelian group, so it must satisfy the associativity. So I can transfer this bracket of alpha 1 plus beta 1 to the elements beta 1 plus gamma 1, as well as for this second coordinate also alpha 2 outside plus bracket beta 2 plus gamma 2 and so on dot dot alpha n plus bracket. So in this way I can separate it out. I can write down in first bracket alpha 1 and so on dot alpha n plus in second bracket I can write down addition of these two, but these two are nothing but what, v1 v2 plus v3 and this one is v1. So what we have proved here, we have proved that this v1 plus v2 in bracket plus v3 is same as v1 plus in bracket v2 plus v3, means we can exchange the bracket here. Alright, so this is the associativity with respect to addition. Now one can again observe here that 0 which is equal to 0 comma 0 comma 0 acts as an identity element, because one can observe again with 0 plus v1 is same as v1, means in 0 if you add any element you will get that element. That's why here with respect to addition 0 comma 0 comma 0 n times here becomes an identity element in V. So once we have an identity element, one can find out inverse for non-zero vectors. So minus V1 represents like this, means coordinate wise you can multiply here minus alpha 1 comma minus alpha 2 and so on dot dot minus alpha n is an additive inverse for V1, where V1 is what, V1 is known to you, which was alpha 1 comma alpha 2 and alpha n, means inverse of V is nothing but it's minus times that V1, because if we add these two, here you will get 0. That's why this minus V1 is an inverse for V1. Hence we have proved here that V is an abelian group with respect to addition operation, right? Now with respect to the scalar multiplication, one should prove the 4 axioms of as in the definition of vector spaces. So let's see first one, alpha into v1 plus v2 is same as alpha v1 plus alpha v2, that we want to show. This is our claim. Now let's see, alpha into v1 plus v2 equal to v1 is known to you, that is alpha 1 and so on dot 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 alpha n, plus v2 is beta 1 comma and so on dot dot comma beta n. First of all I need to add these two vectors, because I have to first solve bracket here, right? So I have to add these two. What is the addition of two vectors here? Alpha 1 plus beta 1 comma alpha 2 plus beta 2 comma and so on dot alpha n plus beta. Now this becomes one vector, single vector, one vector, or you can say single vector in V. Now we can multiply this alpha with this vector. Now what is multiplication? How it is defined? It is defined that you can multiply this alpha to each coordinate. So here I am doing the same, alpha into this first coordinate alpha 1 plus beta 1 comma alpha into alpha 2 plus beta 2 comma and so on dot dot alpha into alpha n plus beta n, right? Now as you can see here that alpha 1 beta 1 are the elements of field, and in the field as field is a ring, you can use which property? Distributive property here, right? So alpha into alpha 1, alpha into beta 1, Same here, alpha into alpha 2, alpha into beta 2, and so on dot dot. Again, after writing this, I can separately write down the terms of alpha 1, alpha 2, alpha n in one bracket. That is alpha alpha 1, comma alpha alpha 2, comma and so on dot dot alpha alpha n in one bracket, plus in the second bracket alpha beta 1, comma alpha beta 2, and so on dot dot. Now we can observe that this is a multiplication. This is a multiplication of alpha with alpha 1, alpha 2, alpha n. Again the same way. So what I got here? I got that alpha into v1 plus v2 is same as alpha v1 plus alpha v2, right? That is the what we have proved. We have proved the first axiom. Now what is second axiom here? See here, alpha 1 alpha plus beta into v1 is same as alpha v1 plus beta. So consider here alpha v1 is alpha 1, alpha 2, alpha n, and alpha beta are the same here. Okay. Now as alpha plus beta is an element of field, I can multiply this element of field with element of vector as defined above, that alpha plus beta into alpha 1 is the first coordinate, comma, and so on dot dot alpha plus beta into alpha n. Finally I can write down. Now as alpha beta alpha 1, these are the element of field, I can again use the distributive law here. Okay, then what I will get, alpha alpha 1 plus beta alpha 1 and so on dot dot alpha alpha n plus beta beta n, right? Now in the same way I can separate it out and I will get this one, alpha alpha 1 comma and so on dot dot alpha alpha n plus beta beta alpha 1 and so on dot dot beta alpha n. So you can separate it out again, because this is a multiplication, scalar multiplication by alpha to alpha 1 alpha 2 alpha n. This is again scalar multiplication by beta to alpha 1 alpha 2 alpha n. So what I will get finally, alpha v1 plus beta v1. That is the second axiom. In the same way, third axiom is here, that alpha into beta v1. As you can observe here, alpha into beta. Beta is a scalar, multiply it with vector, and multiplication is defined as you can multiply that beta with each coordinate here. Then again this becomes a vector, and this alpha is a scalar. You can multiply that scalar with the vectors by multiplying each coordinate. Now as all the alpha beta and gamma alpha beta and alpha i's are the element of field, you can rewrite this with the property of associativity. You can write down this one, and after rewriting this you will get final result. Okay, so thus we have proved the third, and fourth one is easy one, as v1 into v1 is v1. How to prove this? 1 into v1, where v1 is what, alpha 1 alpha 2 alpha n. Now 1 into means you are going to multiply this 1 with each coordinate. Now multiply there. Now 1 is an element of field, alpha 1 is an element of field, so 1 into alpha 1 is alpha 1 and so on dot dot 1 into alpha n is an alpha n. So thus what we got here, again v1. That's why 1 into v1 is v1, and it should happen for all v1. Okay, yeah, it happens. Okay, now hence V forms a vector space over a field F. Since it will keep reappearing, I am going to give notation for this vector space, namely as F raised to n, because we are considering here ordered n tuples. That's why I am writing here F raised to n. If someone consider set of all ordered pairs, then it will be what, F square, right? Okay, so let's go ahead with the next example, which is example on set of polynomials. So as we know that we are going to define a vector space over field. So first of all, let us consider a field. Let F be any field. And what is V? V is nothing but f of x. F of x means what? Set of all polynomials over f. Set of all polynomial in x over f, and it forms a vector space. Now one can easily observe, one should know that because already you have learned in ring theory that V equal to f of x is a ring. It is a ring. That's why automatically it forms a abelian group with respect to addition. Now with respect to multiplication, or you can say with respect to scalar multiplication, it should satisfy those four axioms of vector spaces, right? That is the thing only you have to prove here, right? That means you can multiply element of f, and what is how the multiplication is defined here? Multiplication of element of field with element of say here vector is defined like you can multiply that scalar with each coefficient of a polynomial. See here, V is what? V is set of all polynomials, means you will have one polynomial, and suppose alpha is one scalar. Then how to take the multiplication here? Now suppose you have multiplication here alpha, and suppose one polynomial is there, say x square plus 2x. okay, this is one polynomial. So what will be the scalar multiplication here? Scalar multiplication is nothing but you can multiply this alpha with each term, right? See here, alpha x square plus 2 alpha into x, right? So this is a scalar multiplication here defined. Okay, now with respect to this scalar multiplication, it satisfies all other four axioms of vector space. That's why this V forms a vector space over field F, right? Now this next example is a particular example of this previous example. See here how in f of x, let Vn, here I am denoting Vn is what? Set of all polynomials of degree less than n. Means here I am restricting over the degrees of polynomial. So I am considering here Vn is what? Set of all polynomials of degree less than n. Right? What happens if I consider the degree exact equal to n? Whether it will be it will form a vector space? No, it won't form a vector space. What I am saying, if I consider the set of polynomials of degree exact to n, what will happen at that point? Because if we consider the degree polynomials, suppose p of x and q of x, only suppose p of x is there. Okay, p of x is there, then what about p of x in minus p of x? P of x minus p of x will be 0, and 0 is a polynomial of degree, yes, polynomial of degree what? 0. That's why closure property doesn't hold there. Are you getting? So if we consider the set of all polynomial of a degree say 2, then if you consider the same polynomial and subtract it from itself, then you will get 0. You will get 0 means 0 has to be in V, but 0 is of degree 0. So their closure property doesn't hold. That's why here the set of all polynomials of degree n won't be a vector space. Alright, that's why what we have considered here, that Vn be the set of all polynomials of degree less than n. Okay, yes. So using natural operations of polynomials, obviously with respect to addition, that Vn is a vector space over F. Now one can observe the relation between this example and the previous example. That previous example is a bigger set, because in the previous example we haven't restricted what, the degree of polynomial, right? Yeah, you can see here this is a set of all polynomials of no means there is no restriction over the degree of polynomial, right? So this is a bigger set than this Vn, because here we have restricted over the degree, right? That's why what I can say, this example 4.1.4 is a subspace, or I haven't defined the definition of subspace yet, but this is what subset of 4.1.2 here. Okay, now one can observe here Vn is what, Vn is set of all polynomials of degree less than n, means the polynomials will be of this form: alpha naught plus alpha 1x and so on dot dot alpha n minus 1 x raised to n minus 1, where all alpha is are in F, right? But you can observe here, you can collect for each polynomial we will get such coefficients, right? But as the degree of polynomial is strictly less than n, so the how many coefficients will be there? There will be n coefficients like this, right? That means what I am getting, for each polynomial I will get ordered n tuple. For each polynomial I will get ordered n tuple of this form, right? That's why one can observe here that this Vn, right, this Vn is isomorphic to f raised to n. As we know that f raised to n is a vector space, and how the elements of f raised to n look like this, ordered n tuples. So for each polynomial we have ordered n tuple, as well as for each ordered n tuple I can write down one polynomial. So there is a one-to-one correspondence between Vn and f raised to n. That's why both of them are isomorphic as vector spaces. Okay, so the last example, that is an example of a set of all matrices of size m by n over k. Over k means what? I am going to consider the entries of those matrices from field k. Thus the set of all such kind of matrices having same size, see here I am considering the set of all matrices of size m by n, and it forms a vector space over k. Now to form a vector space, first of all I need to define the addition operation. So if the matrices having the same size, then we can add easily, right? We can add corresponding entries here. So that is the addition defined, and with respect to this addition, this k raised to m by n is an abelian group. One can easily check it out. And what is the scalar multiplication? See here, lambda into matrix means what? How I am going to define this? See here, I am going to multiply this scalar with each entry in matrix A. This is a scalar multiplication. Now with respect to this addition and this scalar multiplication, this k raised to m by n forms a vector space over field k, because entries of that matrix are belongs to field k.